स्टार्ट करो। हो गया है? लाइव गया अपन?
हाँ सर।
दिख नहीं रहा है इसमें। हेलो स्टूडेंट्स, वेरी गुड इवनिंग। हाय प्रधान जी। हेलो स्टूडेंट्स, आज बहुत ज्यादा ही इंपॉर्टेंट दिन है। आज हम करने वाले हैं ऑर्गेनिक केमिस्ट्री का। आज हमारा पहला लाइव है। इतने दिन तो हम लोग इनऑर्गेनिक और फिजिकल केमिस्ट्री कर रहे थे, ओके। बट हमको अगर केमिस्ट्री में अच्छा स्कोर करना है, बहुत ज्यादा इंपॉर्टेंट है हम लोग ऑर्गेनिक केमिस्ट्री में भी बहुत अच्छा करें, ओके। जेई नीट लेवल पर, हर एक लेवल पर। तो आप सोच रहे हो कि मैं क्या कर रहा हूँ इधर। एक्चुअली मेरा कुछ ज्यादा काम है नहीं। हेलो साक्षी, हाय, हेलो एवरीवन, जल्दी से ज्वाइन हो जाओ, ओके। बहुत ही ज्यादा इंपॉर्टेंट लेक्चर है स्टूडेंट्स, ओके। आपका जो भी ऑर्गेनिक का जो भी इश्यूज जो है आज के आज पीवाईक्यूज के साथ जो है हम लोग सॉल्व करने वाले हैं। तो अपने कॉपी लेकर बैठ जाइए और फट से फट जो है नोट डाउन कीजिए, बिकॉज आज हम लोग एक नए सर को जो है ऑनलाइन में जो है लेकर आने वाले हैं। सो लेट्स ऑल वेलकम सर, कम इन। सुनील सर इज हियर and Sunil sir is going to help you with all your isomerism issues. तो जो भी आइसोमेरिज्म में जो भी प्रॉब्लम आया है, ओके, सर आपको पूरी तरीके से ऑन पॉइंट इन डिटेल पढ़ाने वाले हैं, है ना सर? आज एकदम जो है पूरा हम लोग धमाल करने वाले हैं। यस, अगर पूरा ही ये लोग अगर बैठते हैं लेक्चर में, आप क्या बोलते हो, पूरा आइसोमेरिज्म समझ में आ जाएगा?
Very much, why not?
है ना?
Yeah.
तो सर क्या हम लोग आज पीवाईक्यूज भी करने वाले हैं?
Yes, why not?
Yes.
We should.
यस, तो हम लोग पीवाईक्यूज भी करेंगे स्टूडेंट्स,
Yeah.
ओके।
Yeah.
तो ऐसे ही लगे रहिए, ओके। सो पूरा लेक्चर यस अटेंड कीजिए एंड डू लाइक एंड सब्सक्राइब एज वेल स्टूडेंट्स। सो दैट्स माय पार्ट, आई विल सी यू, बाय।
Okay, thank you so much, Rahul sir.
ओके सर।
Hi students, very good evening, and today I will start as I just said, isomerism. Okay. So first of all, I just define what is isomerism in organic chemistry. Done? Yes. I'm just writing it down on the board. Just see. Isomerism is a phenomenon. Isomerism is a phenomenon. Isomerism is the phenomenon in which two or more compounds having same molecular formula exhibit different structures and different physical and chemical properties. Physical and chemical properties. Then, see, isomerism is the phenomenon in which two or more compounds having same molecular formula. The molecular formula of each isomer should be exactly the same, and they exhibit different structures. The structures are different, they are not same. Even though they show same molecular formula, the structures will be different. Not only that, they show different chemical as well as physical properties. So when they have different physical and chemical properties, also they have different structural pattern, but having same molecular formula, then such compounds are called as isomers. So such compounds are called as known as, yes, what is that? Isomers. I hope it is clear with you. So isomers are what you just need to remember is that same molecular formula same, structural formula different, physical and chemical properties different. So these are the important points you just need to note down. Molecular formula same, structural formula different, physical and chemical properties different. Okay? Fine. Now, we just move on to the broader classification of isomerism. Okay? The broader classification of isomerism. Isomerism, fine. I just take left side, structural isomerism, and the right side I will take stereoisomerism. Fine. If you look at the board, you can see that the isomerism is broadly classified into structural isomerism, and the second is stereoisomerism. Fine? Good. Today, at this part, today we are going to discuss this part of it, like, the half of it, the left half of it. The right half we will discuss later. Okay? This we will do it later. Today we will discuss on the structural isomerism in detail. Fine? Good. Now, the structural isomerism. Yes. Structural isomerism. What is a simple definition for structural isomerism? It is due to different arrangement of atoms and bonds present in an organic molecule. Because we are discussing organic chemistry, so the isomerism would be with respect to organic molecules. So structural isomerism is due to different arrangement of atoms and different bonds present in an organic molecule. So when it happens in an organic molecule, we can have different types of structural pattern. Just take a simple classification of it again. Fine. The structural isomerism I will just classify in this way. The first one, chain isomerism, then position isomerism, functional isomerism, then metamerism. Okay, now I just need to get it two more, so you just need to cooperate with me. If you find any difficulty, just let me know. Metamerism, then ring chain isomerism, ring chain isomerism, and one more, the last one, tautomerism. So the structural isomerism is further divided into 1, 2, 3, 4, 5, 6. 6 categories, isn't it? The first one is chain isomerism. Second part is position isomerism. Third one is functional isomerism or functional group isomerism. And the fourth is metamerism. Metamerism. And the fifth one is ring dash chain isomerism or ring chain isomerism. Ring chain isomerism. And the last one is tautomerism. Tautomerism. Isn't it? Just make a note of it. I mean, in the sense what I just written on the board. So then we will go further with the discussion. Ruben Pradhan, okay. Sakshi, good. Good evening. Good evening. Good evening, Sakshi. Sudhi Ambre, hello sir. Yeah. Good evening. Good evening. Okay. Everyone, yeah. Please. Is it clear? The board, I perhaps may not, my handwriting may not be that much good, but I'll try to improve upon that, okay? So I'll just read it out once more. The structural isomerism is the chain isomerism. Second is position isomerism. And third one is functional isomerism, functional. And the fourth one is metamerism. And the fifth one is ring chain isomerism. And the last one, the sixth one is tautomerism. What is that? Tautomerism. Okay? Now we will discuss each and every one in detail. Alright? Fine. So the first one is what? Chain isomerism. So let us have a simple definition of it, because such questions are coming from your JE as well, your CET and even NEET. Such questions are highly expected. So this particular part, each and every part is important, but especially some questions are coming for the last few years continuously from this particular chain isomerism. Okay, so I just make a simple a definition for what is chain isomerism. Okay, fine. It arises due to different carbon chain length It arises due to different carbon chain length of the parent chain or with the side chain This especially happens when it is cyclic. If cyclic structures are attached with small groups, then that becomes side chain. If that side chain is split up into two, for example, if it is an ethyl group, so ethyl group contains what? Two carbons, right? So that can be split up further into two groups as CS3 and CS3. So even such sort of isomerism is possible, and in that the parent carbon framework will be cyclic. So it is more applicable to cyclic part. This is very common, like carbon chain length of the parent chain. Even for aliphatic hydrocarbons, you must have seen, even for other functional groups which contain. So they are all having different carbon chain length, or sometimes with difference in the side chain, or with side chain difference, or with side chain difference. And you have to remember always that the molecular formula is always same. So I don't need to tell you each and every time the molecular formula is same. The molecular formula by default it is same. Whenever we discuss about isomerism, molecular formula is always same. MF is always same. If there are 2, 3, 4, 5, 10, 16, whatever may be the number of isomers, each isomers are having the same number of carbons or hydrogens or oxygens, whatever it may be. That means the molecular formula will be the same. Now, take an example and then that particular concept will be much more clear. Okay? So I'll just take some simple example first, so which you are very familiar with, I guess. For example, if you take this particular compound, CH4. CH4 is the simplest alkane, right? Having carbon number 1. But it cannot have any sort of isomerism because only one type of arrangement is possible with one carbon. Let us take a 2-carbon alkane. Here also you cannot have what? You cannot have chain isomerism because it cannot have different chain linkage. What about the third one? Propane, CH3, CH2, CH3. Here also, if at all you take any of the pattern and link with, you won't be able to get different structural pattern. That means carbon number 1, carbon number 2 or carbon number 3 in these alkanes, that is methane, ethane and propane, I cannot have chain isomerism. It will not show no chain isomerism. Okay. Now, what about the next number? That is carbon number 4. Carbon number 4 is butane, isn't it? When carbon number is 4, that particular alkane is nothing but butane. Okay, fine. Here I can have different structural patterns. I can have different structural patterns. So, what are those different structural patterns? Just see what are the different structural patterns. What are the different structural pattern? Okay? What are the different structural pattern? Fine. First of all, we write the structure of butane. All right? So, can I just write this way? 1, 2, 3, 4. This is bond line formula. You are familiar with, I guess. 1, 2, 3, 4. Yes. Here, I'm just writing 1, 2, 3, 4. I'm just numbering it from left to right. 1, 2, 3, 4. And just say, can I have a different structural pattern of this particular carbon chain? Can I have a different structural pattern of this carbon chain by some sort of breaking off some part and attaching that to any of the positions? All right? Good. Now, if I take this particular CH4, this particular fourth carbon as CH3, and if I attach this with the carbon number 2, then I get a different structural pattern, but the molecular formula is not changed. If you look at the molecular formula, it will be CnH2n plus 2, right? So it must be C4H2n means 2 into 4, 8 plus 2, 10. C4H10, sorry, C4H10. So this is C4H10, this is also C4H10. But what is the difference? This is a linear chain, it's a linear chain or straight chain. So this is a linear chain or straight chain which act as, which is the parent chain. Here in the first structure, I'll just make it as a linear chain or straight chain, which I consider as a parent chain. Now there is no other attachment on this parent chain. Chain. But if I take up this particular structure, 1, 2, 3, the parent chain now becomes 3 carbon. Here it is 4 carbon. Isn't it? Here it is 3 carbon. And one of the methyl group is attached to carbon number 2. That means these two structures having same molecular formula but different structural pattern. Therefore, this particular isomerism is known as chain isomerism. Because why it is chain isomerism? In the chain, you can see some difference. This is a linear chain or straight chain. But here, in the chain, I can have a different branch. So it is a chain isomer of this particular structure 1. So this particular compounds, I just name it as, the first one is N-butane and the second one is isobutane. Is it clear? Yes, it is clear. Tejas, Kadlak, good, yeah. Yeah, 2-methyl propane. Yeah, that's right. Isobutane. Good, good. Yeah. Yeah, that's it. Yes. So this is normal butane, or simply in IUPAC name if you write, we don't put normal, we just put as butane only, right? We just put it as butane. That is the IUPAC nomenclature. So IUPAC nomenclature for isobutane would be 2-methyl propane. 2-methyl propane. 2-methyl propane. Good that you know you are reciprocating in a good way. Fine. Yes. Structural pattern different in these two molecules. Therefore, I would say structure 1 and structure 2, they are chain isomers. They are chain isomers of an alkane having a molecular formula C4H10. C4H10. So I would say this is the first hydrocarbon in alkane series which show chain isomerism. We show chain isomerism. Yes. Now we'll take another example where I can have, one more additional carbon. One more additional carbon. What will be that? One more additional carbon. That will be pentane, isn't it? That will be pentane. That will be pentane. Just take pentane. Here it will be again Cn H2n plus 2. So here C5 H 2 into 5 plus 2. So that's C5 H 10 plus 2 12. So this is the molecular formula. So I can have different structural pattern and especially different chain isomerism. Different chain isomerism with this particular hydrocarbon having a molecular formula C5H12. Let us see what are the structures. So first of all, I just write 1, 2, 3, 4, 5. 1, 2, 3, 4 and 5. Isn't it? So it's a bond line representation and I guess you people are aware of it. Hello? The starting one is carbon. The two bonds which are joining, that is the number 2, that is also a carbon. And the one which is there down, the point 3, that's also carbon. And the one up, that is at 4, that is also carbon. And at the end, that's also carbon. So these are terminal carbons. The extreme 1 and 5 are terminal carbons. Terminal carbons. Fine. Now here, this is a straight chain. So I'll take this as a structure 1, which is having a chain of carbon having number 5. Now, what all the other arrangements I can make with this? In that case, I will have to shorten. This particular parent chain. Then I will get the different isomers. Which isomers? Chain isomers. The easy way to make the other isomers will be take the parent, the long chain one, then you reduce one carbon from this and then attach on suitable positions. Then you will get a second isomer. Okay? So I will take here is 1, 2, 3, 1, 2, 3, 4. Okay? 1, 2, 3, 4. Now, this is now the parent chain. Here it was 5. Now here it is 4. But I have to make sure that the molecular formula must be same. Then here I will add either at position 2 or at position 3 one methyl group. One methyl group. Isn't it? I can keep it here at the third position or I can keep it here at the second position. Both are same. Isn't it? So this is something different from the one. So here the carbon chain length is shortened, that is at 4. Here it is 5. Now, can I have another isomer for this particular structure. Just try out if I can make some rearrangement on this, then can I have some other isomeric forms? Can I have other isomeric forms? Yeah, that's great. Yes, it is neopentane. Good, good, good. It is neopentane. Here see, 1, 2, 3, 4, 5. It's just like an X, right? It's a bond line structure. So this is one carbon, second, third, fourth, and fifth. So I can have 1, 2, 3 structural isomers, isn't it? They are quite different except the molecular formula. Because if you look at the structure, this is 5 carbon long chain. This is a 4 carbon long chain, that is a parent chain with 1 methyl. Here it is, you can say 1, 2, 3. 3 carbon chain with 2 methyl attachment at position 2. So I can have 3 chain isomers. I can have 3 chain isomers, isn't it? I can have 3 chain isomers for pentane. I can have 3 chain isomers for pentane. Okay, is isopentane? Yes, this is isopentane. Exactly. This is isopentane, and this is N-pentane. Okay, and this will be neopentane. Neopentane. So what will be the IUPAC nomenclature for this? Whenever it is N-pentane, you just omit N and just put pentane. So it would be pentane, right? That is IUPAC name. IUPAC, okay? Here the IUPAC would be, you have to start from the right to left because the methyl group comes at the right with the lowest number. So it will be 1, 2, 3, 4. So it will be 2 methyl. And what's the parent chain? Butane. 2 methyl butane. And here, if you look at the structure, you can see what's the parent chain. How many carbons are there in the parent chain? How many carbons are there in the parent chain? 1, 2, 3, isn't it? Yes. And at position 2, there are 2 methyl groups, right? So it will be 2, 2 dimethyl propane. So these are the IUPAC names of the corresponding structures. So we have discussed one with butane, the other with pentane, the other with pentane. Now, can we have some cyclic structures? Because cyclic structures also we have, mentioned here. So what about the cyclic structures? Cyclic structures can also show this particular sort of chain isomerism. Okay. So I'll take a beautiful example, that is this. This is what? This is cyclohexane, isn't it? This is cyclohexane. All right. Now, upon that, I just made one ethyl group attachment. So it is ethyl cyclohexane, isn't it? This ethyl cyclohexane. Because I don't need to put the position because earlier there is only one substituent on that particular cyclohexane. So here, what's the parent chain or what's the main chain or what is the principal chain? The principal chain is this, isn't it? Upon that, CH2, CH3 is attached. Okay. Now, how I will derive a corresponding chain isomer? That comes in the second part of our definition. The side chain can also show different fragments and then attach at different position. That means ethyl can be broken into two. That means if you break at this side, I'll get one CH3 and the other must be CH3. So I will have isn't it? I have, say these two structures are having different side chain length. Before it is 2, 1, 2, isn't it? 1, 2, now here it is 1, 1. Again, I can just make the position change. That obviously would come in the position isomer, but here itself I can show the other arrangement as well, isn't it? The other arrangement as well. So these are all the chain isomers of ethyl cyclohexane. So this would be 1,1 dimethyl cyclohexane. This will be 1,2 dimethyl cyclohexane, and this would be 1,3 dimethyl cyclohexane, and this will be 1,4 dimethyl cyclohexane, isn't it? Fine. So I can have 1, 2, 3, 4, 5 different structural isomers, isn't it? They are different structural isomers with one particular ethyl cyclohexane. Ethyl cyclohexane. Methyl butane, 2-ethyl propane. Hello sir, methane, 2-methyl butane, 2,2-dimethyl cyclopentane. Okay, done. Now we will move on to the next isomerism. That is the next isomerism. That is the second one. Position isomerism. Okay, position isomerism. In this position isomerism, what is important that the functional groups, mainly the functional groups change its position. The functional groups change its position along the principal chain. So position isomerism, I'll write this way: arises due to different positional attachment of a functional group on the parent chain or parent carbon chain. This arises due to different positional attachment of a functional group on the parent carbon chain. In this case, there is interesting to note that it is very interesting that sometimes even a methyl group, when it changes position, it becomes positional isomers. So that is an interesting part, right? So sometimes substituents like methyl, substituents like alkyl group, groups substituent like alkyl groups, when they change their position, then we will get the corresponding position isomerism or position isomers. So let us take some example of this particular isomerism. So I hope you are making a note of it. So position isomerism, it arises due to different positional attachment of a functional group on the parent carbon chain, and even substituents like alkyl group also can act as a functional group, even though in real term we cannot say it as a functional group, but when they change the position, at least in a way we can say that it is acting just like a functional group, just to explain that particular position isomerism. Okay, fine. So for this I'll take some examples. All right. Okay, now so you manage.
हाँ?
I'll manage. I'll call you.
That's it, I'll see. बीच-बीच में मैं देख रहा हूँ.
Fine. Now, positional isomerism. Fine. Okay. Now see. Let us take. I'll interchangeably use condensed formula as well. Bond line formula. So here, if you look at this structure, what is this actually? CS3, CS2, CS2H. It is a hydroxyl group attached to a 3-carbon alkyl chain, isn't it? A 3-carbon alkyl chain. Fine. Now, let us name it 1, 2, 3, isn't it? 1, 2, 3, because OH should get the first preference as per the priority table. So it should get 1 from the right carbon, then it goes to right to left, 1, 2, 3. So here the attachment is at the terminal carbon, right? So this is what? This is 1 propanol, because it is alcohol. So isopropyl, the IUPAC name would be 1 propanol. The IUPAC name would be 1 propanol. Now, as I said, how I will make a different isomer of it, the different isomer with respect to position, isn't it? With respect to position. That means here the position of OH is at carbon number 1. Now I am changing that position to carbon number 2. Then I will have this particular structure, am I right? I'll have this particular structure CH3, CH, OH, CH3. Now here it is at the middle, isn't it? So I can number it from any of the carbon, left to right or right to left. Let me take it right to left, isn't it? So I can have, two different structures in which the functional group changes its position. Here it is at position number 1, here at position number 2, isn't it? So these two are actually what? They are actually positional isomerism or positional isomerism or position isomerism. Position isomerism. Because what is the difference? The difference here is that I have just changed the position of OH group from carbon number 1 to carbon number 2. So this is a pair of positional isomers of this particular alcohol. So 1 propanol and 2 propanol. 1 propanol and 2 propanol are a pair of positional isomers. A pair of positional isomers. Okay. Now let us take another functional group. Say for example, I'll take a halogen. Okay, I'll take halogen and with a carbon number say 4. Carbon number 4. Fine. Carbon number 4 and it being an saturated system, so it is a haloalkene. So let us take this particular structure CS3, CS2, CS2, CS2. 1, 2, 3, 4. Here it is OH. Okay. Now, what you can see here is that the numbering should be 1, 2, 3, 1, 2, 3, 4. So this is 1 butanol, right? Now, I cannot change the pattern of this particular carbon chain. Then that becomes what? Chain isomerism. But we are discussing about what? Functional group isomerism. So in functional group isomerism, I cannot change this particular carbon chain. It should be in the same format, right? But I can only change this OH group position. So this is one. Second, I will write CS3, CH, OH, CS2, CS3, isn't it? CS3, CH, CS2, CS3, CS, CS2, CS3 and OH. Okay, I'll take an alcohol, right? What we are discussing about was a halo compound I will take. So here, I'll just make a halogen here, X. Alright? CS3, CS2, CS2, CS2X. So I've changed the position from here to carbon number 1, carbon number 2. Whether it's possible to carbon number 3? Is it possible to have carbon number 3? Carbon number 2. So 1, 2, 3, 4. If I am taking carbon number 3, CH, OH, CS2, CS3, isn't it? CS3, CH, OH, CS2, CS3. But this is exactly similar to this, isn't it? OH, why I'm keeping on writing OH? It is X, right? It is X. Here, these two structures are exactly same. You know, this is 2 halobutane. This is also 2 halobutane. So I can have these two different structures for carbon number 4 and halogen, right? 1, 2, 3, 4, and here there is an attachment of X 1, 2, 3, 4, and 1, 2, 3, 1, 2, 3, 4. So here I have attachment at carbon number 2. So I have these two types of structural isomerism. This structural isomerism is nothing but position isomerism, because I will change the position of the particular functional groups on the carbon chain. Now, if you look at some different structural isomers, of hexane, okay? Hexane. Different structural isomers of hexane. So what would it look like? I'll use bond line. 1, 2, 3, 4, 5, 6. This is one. That's a straight chain. Now, सर इसका जो पीछे का जो है दैट्स ऑल
पेज
पेज अभी तो रफ किया है, वो तो गया होगा.
might be 1 second.
Yeah.
ज़्यादा पीछे है या अच्छा
ठीक है.
नहीं आया ऐसा.
आएगा.
नहीं वो पूरा क्लियर किया था क्या हमने ये दिस वन
इस सब पीछे.
दिस वन
Yeah, just go back, no? Just go back. Again back. Yes, we have just written that.
दिस वन
No. Again back.
it's a question or what?
No, it's a written matter there, like, like this. Yeah, position isomerism. Yes. Okay. Fine. Position isomerism. Yes, the structures what we were discussing is this 1, 2, 3, 4, 5, 6. Okay. Now here I can have 1, 2, 3, 4, 1, 2, 3, 4, 5, 6, 1, 2, 3, 4, 5, 6, 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, 6. Now I can have 1, 2, 3, 4, 5, 6, isn't it? 1, 2, 3, 4, then I can have one more structure. Okay, this is 1, and here I am just putting that methyl group. Okay, 1, 2, here 3, right. Now here you can say hexane, different types of hexanes. They are all hexanes. This is a straight chain. This is an iso one. This is a dimethyl substituted butane, and this is also a butane which is dimethyl substituted at the second position. Here it is at the secondary part, what we called as 1, 2, 3, 4, 5. That is 3 methyl, 1, 2, 3, 4, 5. 3 methyl pentane. Now here these are all different structural isomers. These are all different structural isomers of hexanes. That means it is again chain as well as it contains some positional isomerism as well. Positional isomerism as well. Just note down this structure and then we will discuss, what are the, pairs which show chain isomerism, and what are the pairs which shows, positional isomerism. Okay, now here all these structures 1, 2, 3, 4, 5. All these 5 structures are 1, 2, 3, 4, 5. All these structures are nothing but chain isomers. They are chain isomers. They are chain isomers. They are chain isomers. All are chain isomers. No doubt about it. Because if you look at the chain, this is a straight chain. Now it is a branched one. This is also branched, but there is a difference in the branching. Therefore, it is a chain isomerism. So, what's the definition of chain isomerism? The isomerism which arises due to different structural pattern of the parent chain. Here, the parent chain would be of 6. Here it is 5. Here it is 4, and with 2 methyl. Here it is 1, 2, 3, 4 with 2 methyl, but at position 2, isn't it? At position 2. So these two are not same, they are different. And this one, this methyl group is at position number 3. Here it is position number 2. Here it is 1, 2, 3, 4. At 3 and 2 methyls. Here 2, 2 dimethyl, isn't it? Here 3 methyl. Here it is 3 methyl. So the position of the methyl groups are changed. So that's what I was telling initially. Like, it is not just only the functional groups. Normally, when we say functional groups, we are having, the hetero atoms like OH, SH, COH, SO3H, and even CN, etc. But in this particular isomerism part, we can take this methyl group also as a functional group type. At least just for this particular positional isomerism. Okay. Now we will see what are the positional isomers of this particular structure. One thing I said, all 1, 2, 3, 4, 5, all the isomers are chain isomers, but whether all these isomers are position isomers, that's what we want to get into and analyze. So what are the pairs of position isomers? In position isomers, you have to make sure that the carbon chain must be same, that parent chain must be same. The parent chain must be same. And at the same time, it must include different position of the alkyl groups. So if I take this particular one, which contains a 5 carbon at a methyl group at 3 and a 5 carbon at methyl group at position 2. So these two are, which one? 2 and 5 are actually, they are position isomers, isn't it? Are you getting my point? They are position isomers. Because the chain length, if you look at the parent 1, 2, 3, 4, 5, here it is a 1, 2, 3, 4, 5, but the methyl is at 3, here the methyl is at 2. That's only difference. That means this particular methyl substituent changes its position from 2 to 3. Therefore, these two pairs are positional isomers. Can I have another positional isomer, another pair of positional isomer? Just see. Can I have another pair of positional isomer? Can I have another pair of positional isomer? Yes, it is possible. Very much. 1, 2, 3, 4. Here it is. 1, 2, 3, 4. That means I have a carbon chain length 4. A carbon chain length 4. Here also a carbon chain length 4. And the methyl groups are at different positions. At 2 and 3. Here is also at position 2 and 2. That means these two are, that is the number 3 and number 4 are also positional isomers, also positional isomers. So in summary, I just will try to tell you that all these are structural isomers, no doubt about it. The structural isomers is at the apex, and then we will just coming down to different category, isn't it? In that case, if I am talking about all these 5 structures, all are structural isomers. Now we will further categorize them. Out of these, which are positional isomer? The positional isomer must be those isomers in which there must be same number of carbon chain with a substituent. Here it is alkyl, but its position must be different. So it is at position number 3, here it is position number 2. Similarly, here it is carbon, it is 4, that is butane type, and it is 2 and 3 position we have 2 methyl groups. Similarly, here at this position at 2 and 2 we have 2 methyl groups. So I would say that this is a pair of positional isomer and this is another pair of positional isomers. So I think this is bit clear to you. And just moving on to some cyclic structures. Just moving on to some cyclic structures. This will be very interesting. Some cyclic structures. Just move on to some cyclic structures. I can have the same type of isomerism. So can I have this? Yes. 1,1-dimethyl cyclohexane, isn't it? Or simply dimethyl cyclohexane. Fine. Now I am changing the position because this is the parent chain. Here chain is in the cyclic form, right? So it's a cyclo form. Here I am changing the substituent methyl. Remember, again I am changing the substituent at position at 3. Here also I change the position at the extreme, isn't it? So I can have 1, 2, 3, 4. 1, 2, 3, 4 structures, and these structures are all positional isomers. Why they are positional isomers? For the same cyclic structure, that is cyclohexane, I have different positional arrangement of that particular substituent, that is alkyl groups. Therefore, all these comes under the category positional isomerism. Okay, so if you take this as an example, say dimethyl propane, cyclopropane, dimethyl cyclopropane, dimethyl cyclopropane. Now I am changing the position of the methyl groups. I am putting it here. Here it is. This is 1, 1. Here it is 1, 2. Isn't it? So I have 2 positional isomers for this particular structure, cyclohexane 1,1-dimethyl and cyclohexane 1,2-dimethyl. I cannot have 1, 3 because that becomes same only, no? If I put this here, if you want to say that it is 1, 2, 3, if I put here, it is exactly 1, 2 only. So if you write the structure in this fashion, that is nothing but exactly equivalent to what? Exactly equivalent to this one, because the structure pattern is not of any difference. So I can have these 2 positional isomers. Positional isomers. Okay. Pentane, propanol, propanol or propan 2-ol. Propan 1-ol or propan 2-ol. Propan 1-ol and propan 2-ol. They are propan 1-ol and propan 2-ol. No? What is that? Propan 1-ol and propan 2-ol. What is the question really? They are positional isomer, isn't it? Propan 1-ol and propan 2-ol are positional isomers. This is 1, 2, 3. This is 1, 2, 3. So Pradhan, it is 1, 2, 3. This is propan 1-ol, 1, 2, 3, isn't it? 1, 2, 3 propan 1-ol, and this is propan 2-ol. They are functional group isomers because the OH group is changing its position, isn't it? So they are positional isomers. So we have discussed two things, that is, one is chain isomer, the second is position isomer. Now the third one is functional group isomerism. Functional group isomerism, or simply functional isomerism. Functional isomerism. In both way, the name is appearing. So it is functional group isomerism or functional isomerism. What actually this particular term means? This is nothing but isomers having same molecular formula, but having different functional groups. See, different functional groups. Here these isomers are having same molecular formula but having different functional groups. Just see what are these class of isomerism taking some functional groups. Okay, so you must be having an awareness of many functional groups, like I would say OH, okay, even halogen X, CN, cyno, even COH, right, and SO3H, isn't it? Even amine, NH2, even double bond and triple bond, they are also are considered as functional groups. And many other, isocyanide, etc. So just see what are the functional group isomerism or functional isomerism. The isomerism having same molecular formula but having different functional groups, and therefore such compounds generally show difference in physical and chemical properties largely. Why I say it is largely? They show, obviously, the isomers show different physical and chemical properties. But when these functional groups are there, and when they are attached to different positions, not different position, they have different functional groups having same molecular formula. They have different physical and chemical properties in a larger extent. Now, just take some examples of that, just to confirm this particular what I just said. What is that? They show different physical and chemical properties largely, right? Okay, so how the functional group isomerism show that particular type of trend. Okay, now I am taking an alcohol and its other isomer, that is ether. Alcohol and ether. Fine. Alcohol and ether. Let us take CH3, CH2, OH. Fine. This is what? Ethanol. Now, what I am trying to change now is that I am getting a different compound altogether, but having the same molecular formula. That means basically I am going to change the functional group. Here it is alcohol OH, alcohol, that is OH, and here I am just making a rearrangement of the structure so that I will have CH3 dash O CH3. Now if you take the molecular formula, that would be same, isn't it? What would be that? C2H6O, right? C2H6O. Here also it must be C2H6O. So the fundamental aspect of isomerism is done. That is molecular formula same, but the structures are different, and this structural difference is with respect to this particular functional group. Here it is OH, here it is oxygen linked to two other carbons. So when it is OH, we call it as alcohol. So this is alcohol, whereas this particular arrangement is what we call it as an ether linkage, C-O C linkage, C-O C linkage. So it is not same, but they are actually different compounds, but having same molecular formula. Now I just want to tell you that some of the properties of it, right? Now this is OH. Oxygen is attached to hydrogen, or let us say hydrogen is attached to a very electronegative oxygen atom. Here I have what? Here I have oxygen attached to C and C. Now if you take the boiling point of it, the boiling point of this alcohol is higher than that of this particular ether. See, that is what I said, how there is a drastic change in its physical properties. So here it is OH, here it is oxygen. This OH can show intermolecular hydrogen bonding. It can show intermolecular hydrogen bonding. If it is having this particular structure, I can have CH3, CH2, OH. I'm taking two molecules only first. Then here, the second molecule, I can have this particular pattern. I mean, H of this particular first molecule is in hydrogen bonding with the oxygen of the second molecule. The oxygen of the second molecule. That is CH3, CH2, OH, CH3, CH2, OH. Just put it a bit more clear. Okay. CH3, CH2, OH, and CH3, CH2, OH. Okay. So I'm taking two molecules and I'm showing that what type of interaction these two molecules are having. So there is a relatively stronger hydrogen bonding, isn't it? Hydrogen bondings are weaker intermolecular forces, right? But here I can say it's a relatively stronger intermolecular hydrogen bonding. Again, this can have with other alcoholic group, the interaction. So the interaction keep on going, so that what I would say that this particular alcohol is having higher boiling point. The boiling point will be higher. BP of alcohol is higher than that of ether, because in ether, if you look at the structure CH3O, CH3, it doesn't have any acidic hydrogen, isn't it? Unless and until there is an acidic hydrogen, see, I cannot write the structure like that. It is a protonated ether, isn't it? So here the structure is like this. So if I take another one, it cannot have that particular strong intermolecular hydrogen bonding. Intermolecular hydrogen. This was an old comment. What was that? Intermolecular hydrogen bonding. That means here I cannot have any sort of hydrogen bonding. So when there is no hydrogen bonding, obviously the boiling point will be lesser than that of the corresponding alcohol having the same molecular formula. And if you look at the solubility part, which is also what I would say, it is also physical property, isn't it? Solubility of a particular molecule in water is physical properties. Okay. Now the same factor plays a role in the solubility because it's an alcohol. So CS3, CS2, OH can interact with water molecule through hydrogen bonding, isn't it? So this is hydrogen bonding between alcohol and water molecule. This causes what? A hydration of this particular alcohol. Hydration increases, solubility also increases. That means this is highly water soluble. But at the same time, if you look at ether, it cannot form any sort of hydrogen bonding, with water, but there may be very little solubility in the lower ethers are concerned. There may be very little what I would say, very little solubility, but it is very less as compared to this particular alcohol. Now I am taking another chemical difference. How the chemical difference plays a role in a pair of isomers, isn't it? So we are talking about functional group isomerism, right? So here if you take this particular molecule CS3, CS2, OH, and it reacts with HI, for example, HI. So what is the product you get? You get, CS3, CS2I, okay, as the major product, CS3, CS2I. Now if you take ether and reacts with HI, so what will be the product? You will get a cleavage of the reaction and you will get CS3OH as well CS3I. That means the chemical and physical properties of isomers are different, isn't it? It's a very clear-cut example wherein you can have the physical and chemical properties are different, isn't it? Here when the same reagent reacts with alcohol, it is converted into the corresponding halo compounds. When this is reacted with an ether, it is undergoing cleavage and one part is getting into an alcohol part, the other gets a CS3I, that is halogen part. Halogen part. It is a halogen part. Okay? Now, let us take a combination of different functional groups. What are the different functional groups? Or we can say alcohol and ether. They are one set of functional isomers. Acid and ester, they are another type. Then I can have aldehyde and ketone. This is a third part. Okay, very commonly occurring isomers, the very commonly encountering compounds, alcohol and ether, acid and ester, aldehyde and ketone. We have already discussed alcohol and ether. Now just take acid and ester. Okay, just take a simplest acid, CS3, CS2, CS3, COOH. Okay, acetic acid. Now HCO OCS3, isn't it? CS3COH, CS3COH and HCO-OCS3. What's the molecular formula? See, this is acid, this is ester. 3 plus 1 4. Here 3 plus 1 4. CO2, CO2, isn't it? And CC. So this is acid and this is ester. This is ester. They are functional groups because they are having same molecular formula. They are having same molecular formula, but if you look at the functional groups, it is RCOOH and this is RCOOR. Here, this H is the simplest one. That is why I just cannot take this R because I have just taken the lowest one. I mean second carbon. If I taken 3 carbon, I can put no CS3 here, isn't it? CS3, CS2, COH. If I take, I can just put CS3, CO or CS3. But since I have taken 2 carbon acid, then here it will be a formate ester. You know, HCOH, formic acid ester, methyl ester or formic acid. So these two compounds are functional group or showing functional group isomerism. Functional group isomerism. This functional group is acid ester functional group. This is an ester functional group. Now, if you look at the reactivity, if you boil it with aqueous NaOH, it will undergo cleavage. This will undergo cleavage, liberating the acid. But here, if you look at, if you boil with CS3COOH with sodium, there won't be any breakage. Rather, it will give a sodium salt. So there is a difference in what? There is a difference in reactivity as well. And the boiling point is also high for this particular acid compared to the ester because it is having a COO minus linkage where it is having an ester linkage. Now acid and alcohol done, alcohol and ether done, acid and ester done, and aldehyde and ketone. Aldehyde and ketone. Just take aldehyde and ketone. Take aldehyde and ketone. Okay? CS3, CS2, COH. So this is aldehyde, right? CS3, CS2, COH. And CS3, C double bond O, CS3. The molecular formula will be 3 plus 2. 5 plus 1, 6, and carbon 1, 2, 3, and oxygen 1. This must be C3H6O, isn't it? C3H6, C3H6O, C3H6O, 3 plus 3, 6, CC, 1, 2, 3, CO. Okay, fine. Now, these are a pairs of functional group isomerism. So I can say aldehyde and ketones are functional group isomers. Functional group isomers are those isomers in which there is a change in the structure of the functional group. That means here it is aldehyde functional group, but here it is a ketonic functional group. In the first case it was OH as the functional group, and in the second one it was COC. In the other pair of examples what we have discussed, it was acid and the other was COOR, that is ester. Now another example we can have is nitrite and nitro. Nitrite and nitro. For example, if you take RONO, okay, this is alkyl nitrite. ONO linkage is nitrite linkage, whereas RNO2 is a nitro linkage. Now the linking pattern is different. That means this R is attached to oxygen of NO2. Here this R is attached to N of NO2. That means this is nitroalkane, whereas this is an alkyl nitrite. Both compounds are having same molecular formula, but their physical and chemical properties will be different. So they also constitute functional group isomerism. Functional group isomerism. Now even cyanide and isocyanide, right? CN, cyanide. Take RCN, RNC, isn't it? RNC. This is isomer of this particular cyanide. There is isocyanide. This isocyanide. This is again functional group. Again functional group isomerism, because the pattern of linking is different. Here it is R is attached to C. Here R is attached to N. Therefore, the linking pattern is different. That means this functional group and this functional groups are not same. They are really different functional groups, and therefore these two compounds are also different. Okay. Now we can have another isomerism, what we were discussing, ring chain isomerism. Okay, ring chain isomerism. Ring chain isomerism. Ring chain isomerism. Ring chain isomerism. This arises due to the linking of carbon in a pair of compounds, minimum a pair of compounds, arises due to the linking of carbons in a pair of compounds showing cyclic form or cyclic structure and non-cyclic structure. Structure, one is cyclic, the other is non-cyclic, isn't it? That is acyclic. So having same molecular formula, but it is having different in that particular pattern of linking of carbons. That means one would be ring, the other would be chain. That means this is cyclic, this is acyclic. For example, the lowest member must be 3 carbon, right? That is CS3, CS2, CS3. This is propane, right? Yes. Now, if I link these 2 carbon together, the N2 carbons, then I can have a structure like this: CS2, 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 like this. That means this one and this. That is the bond line. So here, if you look at the molecular formula, here the ring chain. I'm sorry. Here what I would say, the molecule must be having, the molecule must be having a double bond. There must be a double bond here. Then only it can show this particular isomerism, right? So a double bonded compound with its cyclic pattern. It is cyclic pattern. So here this alkene and this particular cycloalkane are ring chain isomers. Ring chain isomers, right? Now here the number of carbons will be 3 and number of hydrogen will be 3. 3 plus 1 and plus 2. 6. Isn't it? C3H6. That is CnH2n. That is for alkene. And what about this? This is not an alkene, but it is a cyclic alkane. It is a cyclic alkane. So this is having how many hydrogens on each carbon? On each carbon I can have, on each carbon I have 6. That means this is also having C3H6 as that particular molecular formula. But if you look at the structure, one is an alkene having a double bond, the other is a cycloalkane, that is cyclopropane. Cyclopropane and propene, they are cyclopropane and cyclopropane are cyclopropane. Yes, cyclopropane. That's right. Cyclopropane. Rupen Pradhan, right? Cyclopropane. Yeah. Cyclopropane and propene. They are what type of compounds or what type of isomers when it comes under? It arises due to the linkage of carbons in a pair of compounds showing cyclic and non-cyclic structure. If you take some other example, for example, if you take, say, this particular compound, right, cyclobutane, what would be the the open chain structure for this particular cyclic compound, which comes under ring chain isomerism? Can anybody name the name of this isomer? The name of the isomer which shows the open chain structure, because this is a closed one. I will need what? Chain one. So what will be the chain of this particular one? In the chat box, anyone can just put an answer, please. Yes? Anyone can give an answer on this ring chain isomerism? Cyclobutane and the other must be an alkene. The other must be an alkene, right? Yeah, that's it. It's not butane, right? It cannot be butane, Tejas. It cannot be butane. It must be an alkene, isn't it? It must be an alkene. That is CH3, CH, CH2, CH, double bond CH2. Then only this will match, isn't it? It cannot be an alkane. It must be an alkene. Here, 2 hydrogen, 2 hydrogen, 2 hydrogen, 2 hydrogen. So 8. H8. Carbon, C4. C4H8. Then the molecular formula must be matching with that, isn't it? So it cannot be butane. Yeah, it is butene. Yes. They just cut like it is butene. Yeah. 1, 2, 3, 4. Yes, it is butene, isn't it? CH3, CH2, dash CH, double bond, CH2. So these are a pair of isomers. These are a pair of isomers, and it is a ring chain isomerism. Ring chain isomerism. Yes, that's right. Okay. Now, if I have, say, a triple bonded compound, isn't it? I can have a triple bonded compound. Then what would be the type of, pair of isomers? It's very simple, right? Isn't it? Take CH3, CH2, C triple bond, CH. Okay? This is an open chain structure. I want a cyclic part of it. So obviously, we can write 1, 2, 3, 4 carbons are there. Isn't it? So I can, without hesitation, I can write this particular structure. The basic structure I can write cyclobutane, because it is 1, 2, 3, 4. Now that we just have to consider this particular degree of unsaturation. Here the degree of unsaturation, and if you look at here, there's 2, isn't it? And the degree of unsaturation here also must be 2. That means I can have this particular compound, isn't it? Now the cyclic form gives degree of unsaturation, and 1 pi bond gives another degree of unsaturation. So 1 plus 1 is equal to 2. Here there are 2 pi bonds. So the degree of unsaturation will be 2. That means the degree of unsaturation must be 2 here, isn't it? So degree of unsaturation must be 2. That is how many pi bonds are here? See, 1, 2. Here, the cyclic structure, that means this cyclic structure, we consider it is having a cyclic structure of this particular without any double bond, is having a degree of unsaturation 1, plus when a pi bond comes, it comes as 1. So the degree of unsaturation is 2. So in both the cases I have here 2, here also 2. So these are the two individual compounds. One is cyclic, the other is non-cyclic. So if you look at the molecular formula, you can see that HH, H here, 2 plus 2, 4 plus 2, 6, isn't it? 3 plus 2, 5 plus 1, 6. So H6. So obviously carbon is 4, you know that. Here is so carbon is 4. So these isomers, which one? Alkyne and it's cycloalkene. Alkyne and cycloalkene. Alkyne and cycloalkene are ring chain isomers, whereas alkene and cycloalkane, see, cycloalkane are ring chain isomers. So that's the difference. Alkene and cycloalkane, they are ring chain isomers. Here, alkyne and cycloalkene are ring chain isomers. Okay? Now we will move on to the last part of it. The last part of that is tautomerism. This tautomerism is very important. Questions are coming from this section in JE quite often, and sometimes in your NEET as well, CET. Tautomerism. What is tautomerism? It's a new term, probably students are aware of it. It's not very new term, it's an old one, but it's not been come across quite large among students. Tautomerism. Tautomerism means it is a type of functional group isomerism. You can match it with a functional group isomerism. It's a type of functional group isomerism in which a pair of compounds having same molecular formula shows a dynamic equilibrium having different functional groups, but these different functional groups, when I say, they are not fixed as such. If aldehyde and ketones, if you're taking, they are quite fixed. Aldehyde will not change into ketone, but here they undergo a sort of dynamic equilibrium, and one functional group will change into another immediately. So that is why it is called as tautomerism. It is not a fixed one. It is just like it's just like what we call it. So it's in a dynamic equilibrium. It is like we can say it's a reversible reaction type, right? That is, one group is converted into the other group, and it is keep on changing. That means it is in an equilibrium position. So tautomerism is what? It's a type of functional group isomerism in which A pair of compounds having same molecular formula shows a dynamic equilibrium having different functional groups. Okay. Now we will take a good example of it. For example, CS3, C double bond O, CS3, right? Yes, this is what ketone, right? Now, this is alpha carbon, this is also alpha carbon. Now, this is a highly electronegative oxygen attached, or we can say it is having a minus I effect, right? As well, it is having a conjugative effect. It is having a conjugative effect because of the pi bond between carbon and oxygen. So, in a medium, for example, say in an alkaline medium, if you take an alkaline medium, OH minus, what it happens is that this particular alpha hydrogen becomes more acidic. It becomes more acidic. So I am just taking one methyl group at the left side. So what happens is that this particular pi bond shifts on oxygen because of its high electronegativity compared to carbon, and this causes a release of H plus, from the left alpha carbon. That means this H is being liberated as H plus. That means this is highly acidic alpha hydrogen. Then what I'll get is a structure like this. So I can just put this particular equilibrium, that is CS2, and I have a double bond. Here it is C, here it is OH, and here it is CS3. Now if you look at the structure, here it is ketone, isn't it? CS3CO, ketone. But here it is what? Alcohol. And along with that, there is another functional group, that is double bond. So this is enol. Enol means en part is for double bond, all part is for OH. That was, this is an enol. And this is what? Keto, right? The keto is the functional group, right? So when we name this particular tautomerism is known as keto-enol tautomerism. Keto-enol tautomerism. So to show keto-enol tautomerism, the requirement is that there must be a CO group, majorly a CO group attached with a highly acidic hydrogen. When attached with a carbon which is having highly acidic hydrogen. In such case, it can give this particular sort of keto-enol tautomerism. And similarly, aldehyde as well, right? CS2, I am taking one H here. CS3COH. This is an aldehyde, right? So this is, with respect to this is alpha. So this is alpha hydrogen. So alpha hydrogen comes here and this goes here. That means an equilibrium condition, I can just write CS2 double bond C, OH and H. Isn't it? This is also a keto-enol tautomerism. Keto-enol tautomerism. Normally it is not so. It is not given as aldo-enol tautomerism because it is being familiarized with the ketone. So it is nothing but a type of keto-enol tautomerism, like aldol condensation. Even though it is involved in ketones are involved, we never say it is aldol condensation, ketone condensation. We will never say that. It is aldol condensation only, aldehyde only, right? Similarly, we say it is again keto-enol tautomerism. So it shows keto-enol tautomerism. And a very, very good example for this is this particular active methylene compounds, right? Active methylene compound, this particular active methylene compound, CS3, CO, CS2, CO, CS3. Active methylene compounds are highly acidic alpha hydrogen, highly acidic alpha highly acidic alpha hydrogen. Highly acidic alpha hydrogen, because it is flanked with SCO from left and also SCO from the right. That means it is having a double effect. If it is a ketone, it is having SCS3CO, CS3, only one CO. And with respect to this, but here it is this particular CS2 group, which is flanked by two CO groups on either side of it, causes this as highly acidic H. Highly acidic H. That means it can show a ketoenol tautomerism in a greater extent. It can show ketoenol tautomerism in a greater extent, so that I can just write the structure. You take the alpha of it, CS2 double bond. No, not this structure. This is the highly, not this. Compared to this is the highly acidic, right? That's what I said. CS3, I can have CO minus, okay, and the double bond CH dash C double bond O CS3. That means one H, what is being liberated from here, is attached at this position. So I'll get an enol, right? You get an enol. Now, not only this, if you look at this structure, there's an intramolecular, right? There is an intramolecular hydrogen bonding, which stabilizes the molecule again. And this is something, a very unique property, right? That means this particular molecule is highly stabilized. That means the enol content of this particular compound is very high if you compare with a simple ketone and its enol form, or a simple aldehyde and its enol form, because this is a highly active methylene containing compound. As well, it is being, once the enol is formed, it is being stabilized by intramolecular hydrogen bonding. Intramolecular hydrogen bonding. So this particular compound is a very interesting one as far as ketoenol tautomerism is concerned. And another example I can take is this: CS3, C double bond O, CS2, CO, OMe, or CS3. Acetoacetic ester. But acetoacetic ester is not to that extent, because this group is what? Electron releasing group towards this. No? So this may not give that much strong ketoenol formation. Obviously it shows ketoenol formation, but compared to this particular dione, it is less. And this also can give what? This particular CS3, COH, and this is a double bond CH, C double bond O, OCS3, and this particular bonding is there. But the ketoenol content will be more here because it is a dione, isn't it? It's a dione, but this is not a dione. At one part it is a ketone, and the other part it is a ester part. And a ketone, no, it's an ester part, isn't it? RCOOCS3. So it is an ester part. Here it is a ketone, CO and ester. So compared to this particular dione is showing more enol content because of this particular minus I effect as well as a conjugate effect. Here, if you look at the structure again, it can have this particular conjugation from this side too, isn't it? That means CS3, C double bond O dash CH 2, C double bond O CS3. This is the one which we are discussing, right? So if I have that enol form CS3, C OH double bond O CH dash C double bond O CS3, isn't it? Now this can again shift here and it goes here, isn't it? So that means within this molecule you can have this particular sort of a strong, some sort of resonance effect, isn't it? It's a sort of resonance effect. So this makes this now as a OH minus, and then this becomes automatically CO. So it is in the reverse form. It can form a hydrogen bonding. That means this particular diketone is a very good example for a ketoenol tautomerism, in which the enol part is very high. Now, this enol part concept or keto enol part concept is very important in some structural moieties. For example, if you take this, particular molecule, okay, this is a cyclohexanon with 2 double bonds. Now, this can get into ketoenol because if this particular hydrogen is being removed with the alpha position, obviously it's a ketone, so it will be acidic, but it will be much more acidic because once it is being transferred here, this particular structure is possible. That means you'll get a very stabilized benzene type structure, isn't it? Phenol. So this particular resonance also play a great role in stabilizing a particular enol form. And another example, if you can take, is this. A trion, right? Cyclohexane having 3 CO groups. Now I can have a ketoenol structure like this. If this H is going here, I can have this going from here. I can have OH here. If this H is going from here, I can have OH here. That means I will get a very stabilized structure of benzene. Very stabilized structure of benzene. 1, 2, H, isn't it? So it will be a triol, isn't it? Triol in the sense 3 hydroxyl groups on benzene. So it is a highly stabilized molecule. So that means if I have a structure like this is a much more stable enol form compared to this particular trion, isn't it? Because of it can show a very well established stabilized benzene ring and then an enol. This is a enol, but this is when alternate double bonds are coming in a cyclohexane with the 3 pi bonds, then it is a benzene structure which shows aromaticity, and aromaticity is very, very stabilizing factor. Very, very stabilizing factor. Okay. So can we have some questions? करना है? थोड़ा और बात कर ले, थोड़ा 4-5 questions. Okay, let us take a few questions which has been asked previously. Okay.
आपको गर्मी नहीं लग रही?
चालू करो ना.
आपको टेम्परेचर 28 है.
मैंने रखा है.
राहुल सर शायद आपके वजह से.
अच्छा. Some questions regarding structural isomers and conformations. Okay. The question is this. These are previously asked questions. Which of the following is an isomer of CS2, CS2OH. So this is a question which has been asked in a previous entrance exam. Which of the following is an isomer of 1, 2, 3, 4 butan 1-ol, isn't it? The options are given. Option A, CS3, CS2, CS2OH. Option B, CS3, CS2, OCS3. Option C, CH3, CH, OH, CS2, CS3. And option D, CH3, CH2, CO, CH3. So I expect you viewers are having some efforts from your side so that we can have some we can have some some information from in solving these questions, isn't it? So which of the following is an isomer? Which is the following is an isomer of CH3, CH2, CH3, CH2, 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 OH. There are options given A, B, C, D. So can you just comment on this particular this one? It is option C. Okay. Someone has commented it is option C, right? Which of the following is an isomer of? Okay. Which is an isomer of? Good. Of a 4-carbon system, right? How many have done it? I suppose Tejas has come with an option C. Let us see whether it is correct. Fine. Now this is an OH, right? Now if you look at the options, we can have OH functions as well as ether functional groups, and here it is ketone, right? Here is a ketone, and obviously ketone is not in any way connected with alcohol as far as the isomers are concerned, unless and until it is a keto-enol tautomerism. But it's not an enol. So that option D we can just cancel out. And this is all 1, 2, 3. But here it is given about 1, 2, 3, 4. So isomers must be having same molecular formula. So I cannot have this. Then comes this. This is an ether. Alcohol and ether can have functional group isomers, isn't it? Alcohol and ether can act as functional group isomers, like aldehyde and ketone, like ester and acid. But here the thing is that the carbon number is 1, 2, 3 only. Here the carbon number is 1, 2, 3, 4. So I cannot have this. Now the only option which is left is C. So C is the correct option. So this is what type of structural isomerism? Can you please comment? What type of structural isomerism is this? Yeah, great. It is position isomers. Yeah, this is position isomer. It is position isomer because we are just changing the position from carbon number 1 to carbon number 2. So they are position isomers. Great. Now second question we can just move on to. The question is this: the functional isomer of CH3, CH2, CH2OH. The functional isomer of CH3, CH2, CH2OH. So it is an alcohol, right? So obviously something must be clicking, in your, there in your mind, something must be there in your mind, like it is a functional and it is a there is an OH. So you must have some idea about about the answer. So what is that? The functional isomer of CH3, CH2, CH2OH in the given examples, right? So we can have this particular CH3, CH, OH CH3, and B will be CH3 C double bond O CH3, okay, and C I have CH3 O CH3, and option D, it is CH3 dash O CH2 CH3, isn't it? So what would be the likely answer? Because we can get some information from this particular question itself. It's functional isomer, and the functional isomer here it is OH. So obviously it must be an ether, right? So what would be the correct answer? What would be the correct option? C, A, B, C. In option C, how many carbons are there? In option C, how many carbons are there? Ruben Pradhan, in option C, how many carbons are there? How many carbons are there? Only 2, na? But in the given structure, alcohol, how many carbons are there? 3. Then you have to just change that particular C option, and I guess you will get that particular. Yeah, it is D, right? It is option D, right? Isn't it? It is option D, because this OH, functional isomer of OH cannot be OH, so this is not the right one. And functional isomer of this cannot be with a ketone. That these two options we can just cancel out. And you would say here functional group you cannot change the molecular formula. See, what's the molecular formula here? 3, 2, 2. How many? 3, 2, 5 plus 2. 7 plus 1, 8. H8, C3, H8O, isn't it? Here, if you look at, as I said, one student just commented like CH3O, CH3. Here it is C2 only, na? So, in no way this can be functional isomers. So, the next would be a 1 carbon more ether. That would be this 3 plus 2 and 3. 3 plus 2, 5 plus 3, 8. And C3H8O. So, this is the methyl ethyl ether, or ethyl methyl ether is the correct option. That is option D. Good. Now move on to the next one. Okay. It's an interesting one. Which of the following pairs are tautomers? Which are tautomers? Which are tautomers? Tautomers definition you must be knowing it by now. So it is just like this: A CH3 CH2 CHO and CH3 C double bond O CH3. Option B CH3 CHO and CH2 double bond CHOH, and option C C2H5 CO C2H5 and CH3 CO C3H7. It is a propyl group. And option D, it is CH3 CH double bond CH CH3 and CH3 CH2 double bond CH2. Okay, I suppose this is going to be very an easy task for you. Tautomers, especially ketoenol tautomers. That is what is the normal tautomerism, which is being asked quite frequently. So we have a pair of compounds, and you just need to find out which is the actual pair of compounds. One must be a keto or aldo. Keto or aldo means aldehyde or ketone, both are same in that respect. Ketoenol tautomerism. yeah, ketone or tautomerism. It may be ketone or it may be aldehyde, right? So it is aldehyde here and it is ketone here. Obviously, that is not the correct option, right? So Ruben Pradhan given option B. They just given option D. Okay, option D and option B. CS3, CS double bond, CS, CS3. Which are tautomers? Which are tautomers? Yes, they just work on it once more. Just work on it once more. Which are tautomers? Tautomers should contain an equilibrium mixture of a ketone or aldehyde with enol. So you should have two functional groups, a double bond alpha to OH group, isn't it? So this is the alpha, so this is a double bond, and it is 1, 2, 3. Okay, here, oh, that's right, 1, 2, 3. So B, we cannot have B, I guess. Okay, fine, yes, good, yeah. It is CS3CHO, right? Okay, here, this is not possible in no way, because both are aldehyde and ketone. That is not possible. Now here there are two carbons, two carbon. This is aldehyde and this is the enol part of it, isn't it? So obviously the answer is B. Here it is ketone, we cannot work on this. Even with this is a ketone, we cannot have a ketone-enol combination. Here is a double bond, only a double bond, but there is not OH here, and here is also given a double bond. So this option is far away from the answer. So the correct option is B. I guess Tejas is, sir, can you repeat the third option? 1, 2, 3, A, B, C. Okay, fine. See, Tejas, look at here, it is C2H5, C double bond O, C2H5, C double bond O, C2H5, C2H5, C2H5. Can you repeat the third option? Okay, will you ask me to write the option? C2H5, C double bond O, C2H5, C2H5, CO, C2H5. So it's a ketone, right? So it's a ketone. Tejas is a ketone. And this is also a ketone. So you cannot have them as tautomers. You can say at the max they are, position isomers, because there is a keto group is there, and there is CS3CO, and there is 3 carbon over there. And not even position, they are metamers rather, isn't it? They can be called as a metamers. They are metamers. They are metamers, isn't it? Oh, metamers I just skipped. Okay. So they are, in a way we can say they are metamers. So the correct option is B. I hope Tejas is okay with that. Oh, fine, good. Okay. Oh, I just missed one, metamerism as isomer in a hurry. I just brief that. Then we will move on to the next one, metamerism. Metamerism is very simple. Metamerism is when there is a polyvalent atoms like oxygen, sulfur, or nitrogen, or sometimes this particular. That is what I just said. They just once asked this question, I just clicked with this metamerism. If these are there, and if on either side of it if I have different carbon chain length, then I can say they are a pair of which type of isomerism? They are a pair of metamers. So these are a pair of metamers because on either side of sulfur, the carbon number here is 1, here the carbon number is 3. So it's a 1-3 combination. Here it is 2-2 combination. But the molecular formula remains the same. Therefore, this is metamerism. Or metamerism is nothing but different alkyl chain arrangement. Alkyl chain arrangement on either side of oxygen or sulfur or nitrogen, or a special case, what is this? C double bond O. So this is a metamer. Similarly, oxygen comes in the same group, or I would say sulfur comes in the same group of oxygen, so they can have the same property as far as the linkage is concerned. So this is another set of metamers. CS3 is 1 here, 3 carbon, here 2 carbon, here 2 carbon. Therefore, this particular ether is a pair of isomers. They are what? They are metamers. This is ether, and when it comes, sulfur, they are known as thioether. Thio means sulfur. They are thioether, and when it is simple ether, when we have to put oxygen. Similarly, I can have nitrogen even. On nitrogen, if I have this particular linkage, this one, NH, right? This is a secondary amine. Therefore, I put NH. Then I can have this, and this is 1, 2, 3. 1, 2, 3 is 1. So I'll extend this here too. So I have this one. 1, 2, 3, 4. 1, 2, 3, 4. So these are what? A pair of metamers with NH as the functional group. And special cases with CO. This is very important. Even though we consider it is a functional group, when it comes in the chain, right? See, you people just listen to this, this particular, right? Okay. Now, the numbering, I will just do it. 1, 2, 3, 4, 5, 6. Now, this is 3. Now, you will say, the CO is at position 3, and if I have this particular CS2, 1, 2, 3, 4, 5, 6, 1, 2, 3, 4, 5, 6, CS3, okay, fine. Now here, 1, 2, 3, 1, 2, 3, 1, 2, 3, okay, this is 1, 2, 3, 1, 2, 3, 1, 2, 3, symmetrical, right? So let me make it as CS3, CS2, okay. So here it will be CS2, CS3, 1, 2, 3, 4, 5, 6, 7, okay. Here 1, 2, 3, 4, 5, 6, and I'll put it here, CS3, right? CS3, CS2, CS2, CO, CS2, CS2, CS3. 1, 2, 3, 4, 5, 6, 7. CS3, CS2, 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 CO, CS2, CS3, right? 1, 2, 3, 4, 5, 6, 7. So they must be showing isomerism. But what type of isomerism this will be? Now, it's a functional group. So what is the correct numbering? 1, 2, 3, 4. 1, 2, 3, 4. So it is equal, right? So I'll write it. I'll take it from this side. 1, 2, 3, 4. 1, 2, 3, 4. Okay. 1, 2, 3, 4, 5, 6, 7. So it has 4 position keto group. Here I have to number it from here. As far as the numbering is concerned, I have to write it 1, 2, 3. 1, 2, 3 here. Now this is at 3 position and the keto is at 4 position. Now you would say it is position isomer, right? Position isomer. Now, in a way, this is correct. Which one? Position isomer is correct. But much more than that, this can be considered as metamer. This can be considered as metamer. That means when keto group is there, as the metameric example is given, the chain length on either side changes, then when they are ketones, then we can consider them as metamers. That means if metamer is given, then the first option goes to metamer rather than position isomer. If in the option it is given position isomer, you go for it. But if the question is being asked out of the given compounds, which is metamer, and if this combination is given, then you should not hesitate to answer it as metamer, because a position isomer comes as secondary importance only. That means here it is 3 carbon, here it is 3 carbon, here it is 4 carbon, here it is 2 carbon, isn't it? So this particular keto group can exhibit metamerism. It is a metamerism. It is only with a CO. It is only with a CO polyvalent compound, only with metamerism. Because no other group can show this particular sort of linkage. Who is that? Manas Kulkarni. Why meta, sir? Fine. Because this keto group having this particular, this one comes only in the middle of the chain. In the middle of the chain. Aldehyde I cannot say. In the middle of the chain it comes, isn't it? In the middle of the chain it comes. Therefore, on either side, if the alkyl groups are different, then you primarily go with metamer. Because oxygen, when it comes, we say it is metamer. When oxygen comes, we call it as a metamer, isn't it? CS3, CS2, CS2, CS3. We are not saying as a position isomer. We are saying as CS3, CS2, O, CS2, CS3, isn't it? That means when it comes in the middle of the chain, the functional group, then you can have this particular metamerism for this particular CO compound. But it doesn't mean that position isomer is wrong. In a way, both are right, and the more precisely, metamer is given more preference. Because it comes in the middle of the chain. It's not just an aldehyde, or not like a cyano group CN, or not like say carboxylic acid or ester, isn't it? So they are metamers. Fine. Now, another question is this: which of the following is not isomer of C5H10O? Which of the following is not an isomer of C5H10O? Which is not an isomer of C5H10O? C5H10O. Option A, 3-pentanon. Option B, 2-pentanon. All been asked in the previous year, JEN, NEET as well, CET. The questions are of very important, so you will get a practice on this, so that will give you a boost. And D, 3-ethoxypropane. 3-ethoxypropane. See, one is 3-pentanon, the other is 2-pentanon, and the third one is pentanol. It's an aldehyde. It is an ether, 3-ethoxypropane. So this is the molecular formula given. So what could be this particular C5H10O? It can have, you know, CnH2NO form, isn't it? CnH2NO form, and it is applicable for aldehyde and ketone. It is applicable for aldehyde and ketone. That means this represents an aldehyde or a ketone. This represents an aldehyde or ketone. Now I think someone has given the answer, I guess. Manas Kulkarni, D option. Yeah, Manas Kulkarni, D option. Yeah, that's right. This is the correct option, right? Why it is correct option? Which is not an isomer. 3-pentanone. See, here if you look at, they are given pentanone, 3-pentanone, 2-pentanone. 3-pentanone and 2-pentanone. I can have, they can be metamers, or wherever required, you can add position isomer as well. Wherever required, you can just change this metamer or position because it is a ketone. 3-pentanone and 2-pentanone. Now it is a pentanol. Obviously, pentanol will be isomeric with pentanone, isn't it? Because aldehyde and ketones are functional group isomers. So this is functional group isomer with this. This is functional group isomer with having this particular molecular formula. But ethoxypropane, just write down 3-ethoxypropane. 3-ethoxypropane, CH3, CH2, CH2O. What is that? Ethoxypropane. Okay. Ethoxypropane. Propane. Okay. CH3, CH2, CH3, O, C2H5. Ethoxypropane. 1, 2, 3, 4, 5. 3 plus 2 plus 2. 7. 3 plus 2, 5 plus 2, 7 plus 2, 9 plus 5, 14. C14, right? So C14. No, H14, right? H14. 3 plus 2 plus 2. 3 plus 2, 5 plus 2, 7 plus 2. 9 plus 5, 14. So H14. But we need what? H10. Huh? So this cannot be the right option. And the question is asked which is not the correct isomer. So D is the right answer. D is the right answer. Third carbon. No, Manas Kulkarni, you're just asking, no, it is ethoxypropane, isn't it? What is that? That is not the, actually, no, there is some mistake in this option, I guess. It must be 2-ethoxy. It must be 2-ethoxy, isn't it? The question given here it has, the option is 3-ethoxy. So it must be 2-ethoxy. That means, no, it is ethoxy propan. See, this is the one I just guessed like this. CS3O, C2H5, 1, 2, 3. Ethoxy propan ethoxy propan. Which propan? 2, isn't it? It's 2-ethoxy propan. 1, 2, 3 isopropyl, 3-ethoxy propan. Okay, fine, good. How many chain isomers are possible for the alkane? See, this question is important, isn't it? How many chain isomers? How many chain isomers for molecular formula C6H14? C6H14. At least, I can give the numbers. The numbers only if it is asked, but you can just keep it as, in your mind. If it is 4 carbon alkene, it is giving 2. It is 5 carbon, it is giving 3. And if it is 6 carbon, it will give you 5. Right? So this is the carbon number, this one, which is normally being asked. 4 carbon, you will get chain isomer 2, 5 carbon, you will get 3, 6 carbon, you will get 5. That we have already discussed, right? That we have already discussed previously, isn't it? In the chain isomerism of hexane, we have discussed all the 5 isomers. So the correct option is, here the option is given as A, it is 6, B, it is 5, C, it is 4, and D, it is 9. So here the correct option would be 5. I have already done that, isn't it? So what are the isomers? What you have just drawn here? 1, 2, 3, 4, 5. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Then reduce this particular number. 1, 2, 3, 4, 5. That is at position in the middle. 1, 2, 3, 4, 5. Position here. Then 1, 2, 3, 4. This is 5. Now I am reducing to 4. In 4 I have to make 2 more addition of carbon. Here I can make, now the 4 can have another addition of CS3 groups on carbon number 2. So these are the 5 chain isomers of, they are the chain isomers of what? C6H14. C6H14. Yes, that's right. Yes, great. Now, the question is this: which is not metamer? Which is not metamer? Which is not metamer? A, C2H5O, C2H5. This is a good question. CS3, CS3O, CS2, CS2, CS3, C, CS3O, CH, CS3, C, CS3, O, CH, CS3, CS3, and option D, CS3O, C, CS3, CH3, CH3. Okay. So which is not metamer? Which is not metamer? Which is not metamer? So metamerism is, out of the following which of the following is not a metamer? Yes. Which of the following is not a metamer? Okay, one correction I just have to make here. So CS3OCH, CS3OC, CS3 3 times. Which of the following is not a metamer? Okay, any answer? Tejas, good luck 5. Okay. What is that answer for this option? A, B, C, D. Which is not a metamer?
सर अगर इनकेस बंद करना हो तो ये बैल बजाता है मैं आ जाऊँ।
हाँ जरूर या yes options for this, which is not a metamer, which is not a metamer, out of the given, which is not a metamer? Yes, option D. Manas Kulkarni. Option D. Okay. It is not a metamer. This is a metamer. C2H5, C2H5, isn't it? So it can show metamerism. It can show metamerism, isn't it? And this one also can also show metamerism, isn't it? So 1, 2, 3, 4. Okay. Here 1, 2, 3, 4. Okay. Here 1, 2, 3, 4. 1, 2, 3, 4, 5. Ah, yes. Here the question is bit intriguing, bit like confusing. They just ask the question, which of the following is not a metamer? But they should have given the molecular formula as well. But they have not given that, isn't it? Now here the answer you can just reach is this way. 2 carbon, that is C4H10O. C4H10O. Here also 2, 2, 4, 3, 7 plus 3, 10. And 1, 2, 3, 4. C4H10O. And this also must be C4H10O. But here 1, 2, 3, 4, 5. See, 5 carbons are there. So actually it is a bit confusing. So the question has been asked in a very confusing manner. And if that's the case, this is the perfect answer, isn't it? Because with this particular molecular formula, 1, 2, 3 are correct, isn't it? So with respect to that, they are all what? Isomers. They are all metamers, right? They are all metamers, 1, 2, 3, with this particular C4H10O, but this is having 1 carbon extra. That means this cannot be the option. So option D is the correct answer for this. Another interesting question is this. Another interesting question, okay, regarding that particular ketoenol. CH3, CO, CH3 and CH2 double bond CH, OH, CH3. They are dash. Option A, functional isomerism. Option B, I'm just putting a short form, position isomerism. Option C, metamerism. Okay. And option D, ketoenol tautomerism. Ketoenol tautomerism. So look at the structure, left and right, and see in what way they are being connected. Molecular formula must be same. That is why the question is been asked. Isomers. So isomers, whenever say the molecular formula must be same. So you don't need to check whether they are having the same molecular formula. The only thing which we need to find out is that what type they are connected or which type of isomerism they show. Yes, option D. Yeah, that's right. Yes, correct. Fine, that's great. Option D is a ketoenol tautomerism, right? It can form ketoenol tautomerism. The double bond alpha, the alpha H comes here and goes here and it forms its ketoenol. So option D is the correct answer. That is great. So good that you're all having a good grasp on this. That is nice. A simple question. Sometimes in your board exam or even sometimes in a NEET exam, these questions might appear. HCN and HNC. HCN and HNC. They are A, metamer, B, functional isomer, C, position isomer, and D, chain isomer. Fast. HCN and HNC. HNC, right? HCN and HNC, they are dash type of isomer, metamer, Fi, Pi or Ci. Yes? Okay, Manas Kulkarni, functional isomer. Exactly. This Cn and it is Nc. So the linkage is different, right? So they are functional group isomers or simply functional isomers. Exactly. Good. Now, what would be the answer for this? The another interesting question is N-butyl alcohol and isobutyl alcohol. They are asked in the trivial name or common name. They are one chain isomer, two they are position isomer, they are metamer, and they are tautomers. What is the correct option for this? N-butyl alcohol and isobutyl alcohol. Chain isomer, position isomer, metamer or tautomer. One, two, three, four. They just did a search B. Okay. 1B. Pi. Position isomer. Okay. All right. There's a confusion. It's quite common. And Manas said it is a chain isomer. And Rupan said it is chain isomer. All right. Okay. Just see. For this, we just need to get the structural pattern of this particular alcohol, right? One is N-butyl. So write the structure here. CS3, CS2, CS2, CS2OH, right? N-butyl means normal chain. 1, 2, 3, 4. And this is isobutyl, right? So isobutyl would be like this. CS3, CH, CS3, CS2OH, CS2OH. Now here there is a possibility of confusion. There is no big worry on that. You don't have to worry about. It is quite possible. There is a confusion which may happen on such structures. Here the thing is that when we say position isomer, the carbon chain cannot be changed. That means the parent carbon chain should be in the linear form. If it is in this form, it should keep in this form only, right? Then you can have, this OH can come at this position. This OH comes here, then it becomes position isomer. But if you look at this, the carbon chain is reduced to 3 here, see. And there is an attachment of CS3. That means there is a chain has created, isn't it? Therefore, this is actually, what is that? The first one, that is chain isomerism. So this type of confusion is very common with respect to this particular PI and chain isomerism. So I think Tejas, now it is clear. Okay, Tejas, it is clear now. Tejas, please, is it clear now? Say, if it is in the straight chain, position isomer, right? Position isomer means the position of that particular functional group should change. Then it will be position. But I cannot change that particular carbon chain. Then it becomes a chain isomer. Now that this is 3 carbon only and attached to a methyl group. So it is a chain isomer and not a position isomer. And not a position isomer. Okay, good, great. And we have some 15 minutes more. We'll do 2-3 questions again. All right. The number of structural isomers. The number of structural isomers. The number of structural isomers. The number of structural isomers, bracket, open chain and cyclic, open and cyclic, okay, cyclic, possible for an organic compound having molecular formula C5H12, isn't it? C5H12. They are given options 2, then B is 4, C is 3, and D is 5. D is 5. Now read the question carefully. The number of structural isomers, that means all the isomers you can include. And not only that, it could be even open and even cyclic. That means it just include ring chain isomer as well. So you can explore all the possibilities possible for a compound having this molecular formula. So this molecular formula means what? C5H12 means what? You can get some hint from this. It is a hydrocarbon and it is matching with CnH2n plus 2 pattern, if I am not wrong. C5H2 into 5 plus 2. C5H12, isn't it? So it is pentane. Basically it is pentane. Right? So what are the structural isomers? All, whether it is chain, whether it is position, functional will not come because it is an alkene, and metamer also will not come, and tautomer also will not come. So chain and position, and even ring chain, that is also not possible, I guess, isn't it? Because I guess here you cannot have a cyclic structure because it is completely saturated one, isn't it? So how many structures you can draw? You can draw planar structure. I mean the sense open structure. The open structure would be carbon number 5, na? 1, 2, 3, 1, 2, 3, 4, 5. That is a longest chain. 1, 2, 3, 4, 5. 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4, 5. Right? And one more I can have. Yes, this, isn't it? Right? 1, 2, 3, 4, 5. So I have 3 aliphatic compounds, not any cyclic one. They are open chain compounds only because I cannot have any cyclic structure for this. For this particular one, I cannot have a cyclic structure. Suppose this is the one. I cannot take this, isn't it? So if this is the one and I am attaching this here. 2 plus 2 plus 2. 2, 2, 2. 6 plus 1. 6 plus 1 is 7. 7 plus is 10. Now it is what? C12, isn't it? Even though it is carbon number 5. So that means this particular alkane cannot show it cannot show ring chain isomerism. ring chain isomerism. A structure can be only 3. Radhika Shinde, only 3. Yeah, that's right. The option is right. It is 3. Radhika Shinde C. Only chain isomer. Radhika Shinde. Yes, a structure can be only 3. Yes. Radhika, you are right. It is only 3. You cannot have a cyclic structure. Even though it is given just to confuse, this cyclic structure is not possible. The cyclic structure is actually 0 and this is 3. So 3 plus 1, 3 plus 0 is equal to 3. So I have option 3. Okay. Now another question which I can just take it. 2 more questions only remaining. Here the question is like this. The isomerism exists between CS2 Cl CS2Cl and CS3 CH Cl2. Option A Pi, option B Fi, option C metamerism, option D chain isomerism. The isomerism between a dihallow compound. One is 1, 2, isn't it? This is a vicinal dichloroethane. This is a geminal dichloroethane. So they have what type of isomers? Yes. Option 2, option 1. Okay, option 1. Yes, Manas Kulkarni sir, is option 1. Yeah, it is option 1, isn't it? It is option 1, that is option A. Position isomer, because see, these are the 2 functional groups, right? Now, one functional group is going to the carbon where the other functional group is there. That means there is a shifting of functional group. That means one functional group is shifting to another position from a previously occupied carbon. That means there is a shifting of functional group, and shifting of functional group will obviously give what? Functional, but positional isomer. These and these 2 are positional isomer. Here it is, see, they are at the same carbon 1, 2. If you look at like this, they are on same carbon, but here they are on different carbon. Therefore, they are good example of position isomer. Yes, right. They are position isomer. I think this we can take it as a last question. Ketoenol tautomerism is observed in. Ketoenol tautomerism is in option A C6H5 C double bond OH, B C6H5 C double bond O CH3, option C C6H5 C double bond O C6H5, and option D C6H5 C double bond O C, CH3, C6H5 and CH3. Ketoenol tautomerism is in, means out of this you can see ketoenol tautomerism in only one compound, isn't it? You can see the ketoenol tautomerism only in one of these options. What is that option? Just look at the structure and just see. For ketoenol tautomerism, you must have an alpha hydrogen with respect to SO group. And it should not be a phenyl group. And it should not be a phenyl group. In the option, you have to make sure that it is not attached to phenyl group also. What I just want to tell you that if phenyl group is attached, then it will not provide you alpha hydrogen. But if with phenyl, if some other alpha hydrogen providing groups are there, then that is fine. Good enough. Yes, Manas Kulkarni option 1, C6H5. Option 1. Ketoenol tautomerism is in dash. See, the condition is that with respect to keto, I should have an alpha hydrogen. An alpha hydrogen. This is the prerequisite. This is the prerequisite. Then Manas Kulkarni, you just try to figure out which of these will give ketoenol tautomerism. There must be an availability of hydrogen on alpha carbon with respect to keto group. With respect to keto group, isn't it? So which option is the one where I can have an alpha hydrogen? The both sides there are groups, right? Yes, Manas Kulkarni should come up with some answer, okay? Manas Kulkarni, your option, you just have to... Okay. Yes, I need some answer from your side. So ketoenol tautomerism, right? Ketoenol tautomerism में क्या होता है? मतलब with respect to alpha group, alpha, see, this is the keto group, right? So here there may be a group, here there may be a group, maybe it may be a phenyl group, it may be an alkyl group, right? At this side you cannot expect any hydrogen because it is an aromatic phenyl ring. But at this side there may be an alkyl group, but if it is highly substituted, मतलब सब इतना सब्स्टिट्यूट होगा कि उधर अल्फा हाइड्रोजन ना हो, then it will not show ketoenol. So the prerequisite is that there must be an alkyl group with at least one alpha hydrogen. So what is the correct option? What is the correct option? Manas Kulkarni, you just try out, just see. Rupan given as option B, Radhika Shinde option C, and Rupan Pradhan option B. Yes, you have a time left now, 2 minutes. Why you have stuck up? You have done, 2-3 questions on this ketoenol tautomerism. So I'll give some hint. What is this actually? C6H5. It is a phenyl ring, na? See, if you look at this, I can say this option. I am just showing only this. The rest of things you have to apply. See, this is the one, right? Now this is benzaldehyde. isn't it? This is benzaldehyde, right? So where benzaldehyde, this is alpha. With respect to this is alpha position, and there is no hydrogen at all. There is no hydrogen at all, isn't it? There is no hydrogen, isn't it? C6H5CH2 is out, benzaldehyde. So here you cannot have keto-enol tautomerism. Now option B, yes, at the left side, C6H5, this part is not able to furnish acidic alpha hydrogen. So this part is not able. But what about the other part? Yes, it is CH3, right? So when it is CH3, it is an acidic part, isn't it? See, on either side of it you have to look the structure. Here this is attached to CO alpha. There are 3 acidic hydrogens. So when one comes here, the other goes here. So it can give keto-enol tautomerism. And this H, suppose this H in no way can be considered. That is not alpha. This is the H attached to CO. This is a part of aldehyde. That is a part of aldehyde. This is an aldehyde group. Now, if you look at this option, C6H5, this is also phenyl, this is also phenyl, and there is no way it can give that particular keto-enol. Now here, left side is not possible. Here it is phenyl, but here there is phenyl, but there is a carbon here. So there is some hope like whether there will be a hydrogen. But unfortunately, this is completely occupied by 2 other CH3, right? That means even though it is having an alpha carbon, this is not having any alpha hydrogen. So this can also be not able to furnish to keto-enol tautomerism. So the correct option would be option B. Option B. All right. Well, students, I hope you must have got some idea about these structural isomers, and as well some information from discussing the previous year questions. So we will meet soon with some other interesting part of it. Okay, see you and good night.
कंटेंट भी तो देखो।